Hi everyone and welcome to this new video. In this video we will continue with the subject of AC steady-state power, and in this video we will discuss a design example. This is our design example number 1. What do we have? We have a circuit with a voltage source Vs which is connected to R1, and in series with that there is an element impedance ZL. The voltage source is given, the value of that, and the resulting current Is is also given, and both of them are given in amplitudes and not in RMS values. The question in place is the following: determine the value of the required series element Z of L that must be installed in this circuit such that the total real or true power P of the circuit is 250 watts and there is a leading power factor, and the resistor R1 is 8 ohms. So that's very important information here. I will underscore this. So there's a leading power factor, and I need a total true power of 250 watts. So if I know, let me write this down. If I know that the power factor is leading, I can say directly that the theta I, which is the phase of the expression for Is, is larger than 0. You might ask, why is that? Yeah, the current Is must lead the voltage if you want to have a leading power factor. Since the phase orientation of Vs is 0 degrees, the theta of I must be larger than 0. If this is, for example, 200 cosine 1000 pi t plus 70 degrees, then theta of I must be larger than 70 degrees to meet the condition of leading power factor. So in this case it is 0, so we must be larger than 0. And again, for the calculations for the power, as we know from the previous examples, we need the RMS values, also for the voltage source and also for the resultant current. So let's first determine those two. So the Vs RMS will be the Vs amplitude divided by the square root of 2. We already know that. And that is 200 divided by square root of 2 will be 141.4. And if you write this down in the phasor notation, which will bring us to 141.4 phase 0 degrees. If I continue with the resulting current, Is, also in RMS, which will be Is, the amplitude of that, divided by the square root of 2, and it will be 7 divided by square root of 2 will be 4.95 amperes. Again, expressing this in phasors, Is of R in RMS values will be 4.95 phase. Remember, is theta of I. Okay, now I have those two expressions, and the next step is actually looking at the circuit and determining actually the required value for the ZL. Since it is a leading power factor, I already know that there is a capacitive circuit. So this complete circuit must be capacitive, cannot be inductive. If it is an inductive circuit, then I have a lagging power factor. But I don't know if it is a pure capacitor or is it a combination of the resistor and a capacitor, so that's not really clear at the moment. So I will say in general, so PF is leading, thus in general ZL must be capacitive, or Z in total, so that's actually total resistor. So I can say total impedance ZL, I can write it down as R2 minus JXC, and R total impedance is the summation of R1 and ZL, which is, of course, written in another form as Z is equal to R1 plus R2 minus the J of X of C. So if I now designate the real part. So this is the real part, this is the real, and this is the imaginary part. And I can use those for further calculations for determining the R2 and also the value of the capacitor from the reactance of the capacitor. Still, I don't know yet if the R2 is 0 or not. I don't know yet. So I just use the general formula, general expression. I will see later on if there is a 0 or maybe an additional resistor R2. Okay, this is actually the situation for this case. Now let's start and continue now with the power, which is dissipated power, P, which is of course equal to IS RMS squared times the real value or real part of the total impedance. So real part of the total impedance is R1 plus R2. I know the IS RMS, which is given here. I only use the amplitude. We already discussed it in the previous examples. And this is 250. So if I substitute everything, I know. So it's 250. So it's 250 is equal to 4.95 squared times R1 plus R2. Of course, we know R1 is just 8 ohms, but I will just leave it like this. What we have is the following: R1 plus R2 is equal to 10.2 ohms. That means R2 is not 0 because this is 8. This must be 2.2, such that I get a 10.2. If this was R1 plus R2 8 ohms, then obviously R2 must be 0, otherwise I cannot satisfy the equation. So I have the 8 here, and then R2 is equal to 10.2 ohms, and this will give us R2 is 2.2 ohms. So I already know one of the components of ZL. Then other ones, next one is the capacitor. So let's move on with the value for the capacitor. How do I determine the capacitor value? I can use the phase, but I can also use the magnitude. About the phase, I have not much information, but I know the magnitude of the impedance. The magnitude of the impedance can be calculated using Ohm's law, because the impedance between these two nodes of the voltage source Vs is the voltage source itself divided by the current it is injected in the circuit. So what I can say is the following. I can say Z, the magnitude of that, is equal to the Vs RMS divided by IS RMS, just using Ohm's law. So what do I get? This is 141.4, just in magnitudes, of course, so I don't bother about the phases, and 4 divided by 4.95. So what do I get? I get 28.6 ohms. This is just the magnitude of the impedance. Now, if I now set up an equation for the magnitude of the impedance using this formula and equate this to this value, I can now calculate XC. So let's do that. It's the following, and then I can now do Z absolute value of that is square root of the sum of the resistors R1 and R2 plus the X of C squared, and that is of course equal to the 28.6. Now I already know the R1 plus R2, which is 10.2 squared, so if I now fill in the values, so 10.2 squared plus X of C squared is 28.6. Now the calculation of this is really straightforward, so what I get is 26.7 ohms. So the reactance of the capacitor must be 26.8 ohms. Now I am really close, really close, because now I have to do the following thing: calculate the capacitor value C using the formula, which you already know is capacitor reactance X of C is equal to 1 over omega times C. And I know now the value of X of C is 26.7. I also know the omega, because this is given in the question, which is shown here, is 1000 pi. 1000 pi, of course, both of them. Otherwise, we cannot use a steady state analysis here. If if you have different frequencies. So this is 1000 pi times C, which is unknown of course, and the C can now be calculated, and that will be 11.9 microfarads, almost 12. And it's actually the whole situation here for this design example. So we have calculated the resistor R2 and we have calculated also the capacitor, required capacitor. What you have is following for the ZL. ZL is this, if you express this again, is R2 minus JXC, which is 2.2 minus J 26.7 ohms. This is actually this whole picture. And again, if I now draw a picture of this, just to illustrate the concept in more detail. So I have the following. I have the real axis here, and imaginary axis here. The total real part, so this is again total impedance. This total impedance diagram. So if I have this, which is R1 plus R2, which is 10.2 ohms, and the imaginary part, which is of course much longer, but that is not to scale, so this 26.7 minus J, of course, 26.7, and the factorial sum of this will give us the value of Z, which is shown here, and the phase here is, I will call it phi. So phi is equal to the arctangent of minus 26.7, which is just geometry here, divided by 10.2. And if you calculate this out, you will get minus 69 degrees. Now the question, if this still is this still a leading power factor? Yes. Why? Because the phase of the impedance and the phase of the current has a minus sign with each other. So if the current has a phase of minus 10, then the phase of the impedance will be plus 10, and of course the other way around. So I already know that the theta I must be minus the value what we have here, minus 5, so that will be plus 69, and it will also prove that we have leading power factors. And it's actually just a check that our design is complete and also satisfying the power factor of leading. Alright, this for this example, design example number 1 about AC steady state power analysis. So I hope this will again add valuable information about how to design this kind of circuits and this kind of questions, how you can tackle this. So go through it again. If you have questions, let me know, and I will see you next time, and have a nice day.